Hi everyone, I decided to make a video specifically for this problem. So today we're going to look at use squeeze theorem to show that the limit as x approaches 0 of sine x over x is equal to 1. So the general idea behind squeeze theorem is to show that some lower bound function, or some lower bound, and it happens to be a function, is less than or equal to, let's call this fx, the function that we're interested in. So the function is greater than some lower bound function, but it also happens to be less than some upper bound function. And if you can show that the limit of, in this case, x approaches 0, so if we said the limit is x approaches 0 of the lower bound function, and we also apply that limit to the upper bound function, we can say that the limit as x approaches 0 of the middle function should be between or equal to these two numbers. So that's the idea behind squeeze theorem. Let's take the range of sine x. So we want to generate these functions. So we'll take the range of sine x. We know that sine x is greater than -1 and less than 1 at all times. We can, in order to get sine x over x, we could try dividing everything by x. So when we do that, we get -1 over x is less than or equal to, maybe, sine x over x is less than or equal to 1 over x. So we're not exactly sure if this is true anymore, because x is either, we don't know if x is positive or negative. And if it happens to be negative, then this wouldn't be true anymore because these inequality symbols get flipped. So we have to look at a different way of doing this. So similar idea, we have to generate some lower bound function and an upper bound function, and we have to look at whether this is true. So in order to do that, we have to compare areas by using geometry. So here I already set up a unit circle, and I'm just going to draw a line and this angle. This angle is going to be x. So where this line meets this circle, this is my xy. A little confusing, but like not the angle x, but yeah. And as it turns out, because of trigonometry, that this x coordinate is cosine x. Or maybe not. Let me justify it. So if this is hypotenuse, this is a unit circle, right? So that means this hypotenuse length is 1. And so if I drop down a line here, and so this is a right triangle, right? So this distance right here, it's going to be, this is my adjacent, right? A, and then this is my opposite to my angle. So this is O. So if my adjacent is, let's see, SOHCAHTOA. So my adjacent and my hypotenuse, this is, so cosine x is equal to my adjacent A over my hypotenuse, which is just 1. So that means this is just cosine x, because, yeah, cosine x is just A. And if we do the same thing with the sine, so sine x is equal to the opposite, so O, over the hypotenuse, which is just 1. So sine x is my opposite angle. So that means this is actually cosine x, because this is my x value. I'm cosine x units away from the origin. And then my y value was sine x. I am sine x units away from the origin in the y direction. So this is my coordinates for this. So we have a triangle, right? So we have a triangle. Like something like that. And this distance is cosine x. This distance is sine x. And this distance is 1. What we're interested is in the area of the triangle, right? So area of a triangle is equal to 1/2 base times height. So the area of the triangle is 1/2. The base is cosine x, and my height is sine x. So area of the triangle is this. So I drew a triangle out of this unit circle here, right? But there's also a sector. So this sector, this whole thing. So up until the little end. What's the area of the sector? Right, where this angle is x. Oh, this angle is x. Sorry. So this angle is x, right? This length is 1. This length isn't cosine x. This length is also 1. Right? And it turns out the area of a sector is equal to theta over 2 r squared. Right? And theta, that's our angle, right? So our angle is just x, and then over 2. And then r, our radius, is just 1. So that's 1 squared. So it's just x over 2. And if we look at, so we have the area of the triangle, and we have the area of the sector. And the area of the sector, like, it contains the area of the triangle. So that means the area of, let me see if I can draw. So let's see. So the area of the triangle, that's this area, right? So the green area contains the red area, so that means the green area has to be larger than the red area. So the sector has to be greater than the triangle. So we can say, so the area of the sector is greater than the area of the triangle. And we just plug in. So x over 2 is greater than 1/2 cosine x sine x. And then let's do some algebra to manipulate this in a way that we can recognize. They all have 2, so I can get rid of that. I will, let's see, so I have x over, or is greater than cosine x sine x. I can divide both sides by x. Cosine x sine x over. The reason why I can do, let me finish writing that down. So the reason why I can divide by x in this case is because x is an angle, right? And we know that the angle is positive. And then we can divide both sides by cosine x. So 1 over cosine x is greater than sine x. And the reason why I can divide by cosine x, actually, so the reason why I can divide by x is because I'm stuck in the first quadrant. And angles, and the reason why that's important is because I don't know whether if I'm dividing by positive or negative. So I need to distinguish whether it's positive or negative. So if I look at, I'm just in the first quadrant. The first quadrant is from 0 to, well, pi over 2. So it's always going to be positive. And then cosine in this first quadrant is also always going to be positive, so we're good. So now we have over x. Now we have this fact. We have that, let me rewrite it. So sine x over x is less than cosine x. So what we've effectively done over here is we've generated this upper bound function. So the upper bound function, so let's see, we have sine x over x, and that's less than 1 over cosine x, right? So we've got the upper bound function. We need to generate the lower bound function right now. We don't know what that is. So in order to do that, similar strategy, we just look at areas and we compare. So if we go back to this picture, let me redraw it. Okay. So back to the same picture where this was angle x. So I'm going to plot a point here and then extend it out like this. Right? So something like that. Maybe not like that. Something like this. Yeah. So now we have an even larger triangle, right? Now we have an even larger triangle. So let me draw this triangle in a different place. Let's look at the dimensions of this triangle. We know that this distance here is 1, so that means this is 1. This is a right angle. This angle is x, and using trig we can find what this angle is. Let's call it y. We don't know what it is. So this is the opposite side, and this is the adjacent side. So what we need is tangent TOA. Tangent x is equal to the opposite, which is y, over the adjacent 1. So tangent x is just y. So that's why this is tangent x. And then, just like before when we looked at the areas, let's look at the area of this triangle. So the area of the triangle is equal to 1/2 base times height. So the area of the triangle is equal to 1/2. The base is 1, and then the height is tangent x. So 1 times tangent x. So the area of the triangle is equal to tangent x over 2. Let's see. And then we know that tangent x is equal to sine x over cosine x. So this is really sine x over 2 cosine x. So why does this matter? We can look at the sector. Yeah, let's look at the sector again. Yeah. So now we can compare areas again. So again, we have the area of the sector. So this red shaded area. And we said that the area is equal to x over 2 over here. So the area of this sector is x over 2. And then we have the area of the whole triangle. Right, so the area of the whole triangle is sine x over 2 cosine x, which we determined over here. So now we compare areas. This triangle contains the red area. The green area contains the red area. So we know that sine x over 2 cosine x is larger than x over 2. And then we can do some algebra to manipulate it in a form that it looks like what we started with. So I'm going to get rid of these 2's. I'm going to divide by x and multiply by cosine x. So sine x divide by x. And then, well, I guess there's too many steps. Cosine x is greater than 1. And then I can multiply both sides by cosine x. So sine x over x is greater than cosine x. So let's take this fact and then bring it up over here. So we said that sine x over x is greater than cosine x. So that means cosine x is less than sine x over x. So less than cosine x. Right? So now we can finally evaluate the limit. Let's take the limit as x approaches 0 of this entire thing. So the limit as x approaches 0 of cosine x. That's the same thing as cosine 0. Is less than and then 1 over cosine 0. I guess I could write it like this. The limit as x approaches 0, sine x over x, and then 1 over cosine 0. I know that this cosine 0 is just 1, and then the limit as x approaches 0, sine x over x, and then 1 over cosine, that's 1 over 1, which is just 1. So we've shown that this limit is between 1 and 1. So therefore, the limit as x approaches 0, sine x over x is equal to 1.